Okay, welcome everybody. Um, let's see here. So, got about 6 of you in here so far. It looks like we have 8. So, if you're in here, please go ahead and check in and just comment over on the side, okay? And we will go ahead and get started here. All right. So, I'm going to go right over to where we left off before in our PowerPoint. And so we talked about analog signals and digital signals. We talked about the different number systems and converting between them, all the weighted systems anyway. Hexadecimal, octal, binary, decimal. Right? So now we're going to talk about non-weighted systems. So binary coded decimals. Okay? So it says each of the 10 decimal digits, which that would be 0 through 9. We talked about that last time. So 0 through 9, okay, and get back on the screen, sorry. And then, so the only way that you can get to BCD is through decimal. So if you're in if you're in binary, it only works for 0 through 9. If you have a different number, then you have to go through decimal first to get to BCD, okay? BCD is always a 4-bit binary equivalent. So that means it only counts from 0000 to 1001, which is 9. So it counts from 0 to 9. It only uses the first the first 10 binary digits. Okay, so it does not go all the way up to 1111. So it just says convert each decimal digit to its 4-bit binary code. So it's pretty simple. Okay, I'm actually going to go to the board here to show you the differences. So let's take the number, let's take my baseball number, 29. So that's decimal. Okay, so again, I'm going to start writing subscripts on all these numbers because we go between so many different number systems that I need to be specific about what I'm saying. Okay, so this is 29 in decimal. Okay, now to convert to BCD, so from decimal to BCD, okay, take each individual digit and just convert it to its 4-bit binary equivalent. Okay? What does 2 equate to? Well, that's 0010. That's its 4-bit binary equivalent. 1, 2, 3, 4. 4 bits. Okay? So what's the 4-bit binary equivalent of 9? It's 1001. And remember, you can go to that chart and also lab 1. That's part of your exercise, right? So that is the BCD equivalent of 29 in decimal. It's a non-weighted system, so there's no multiplication there. It's just directly converting. Okay? What's the 4-bit binary of 2? That's what goes first. What's the 4-bit binary of 9? That's what goes next. So we have an 8-bit total BCD number. And so you're only going to have, let's say this was an 8. So that is one possible BCD number, or that's another one. But you always have to have the groups of 4. Okay? And so if you had another one, you could have, maybe you have another, maybe there's a 9 out in front, and then maybe there's a 7. Okay? So this would convert to 7, 9, 3, 8. Right? No calculation whatsoever. So you go back and forth between them. Okay? So that means, I just said, the only way to get to BCD is through decimal. You have to convert it into its decimal equivalent first. So if you're in binary, if you're in octal, if you're in hex, okay, you have to go through here first before you can convert to BCD. And the only way to get from here to one of these, you have to immediately convert back to decimal first. Okay? Any questions on that? Let me go check the chat. right, doesn't seem like we have any questions. So there you go. So again, if you're in any of the number systems, you have to go through decimal first. So you have to convert to decimal. And then once you're in decimal, then you can go to BCD. And if you're in BCD and I ask you to convert that number into hex, then you've got to go into decimal first. All right, so let's do another example of that. So say I want how about 3B in hex, and I want that converted into BCD. Okay? So remember, this is a weighted number system. And as this thing is falling on me again. So I'm going to, this is times 1, this is times 16. Okay? So I got 16 times 3 plus B is 11, so that's 11 times 1. What does that equal? So this is 48 plus 11, so 59 in decimal. So I got to convert it to decimal first, and then once I'm in decimal, then it's just a straight conversion. Okay? So this right here, this is hex to decimal, and now this is decimal to BCD. Okay? 5, 0, 1, 0, 1, 9, 1, 0, 0, 1. Put a little BCD down there. That's it. Okay? So again, once you have it in decimal, it's super easy. It's like the decoder kit from Christmas Story from Ovaltine, where it says drink more Ovaltine. Any questions? Pretty straightforward. I could do that from any number system, convert it, and then as long as I get into decimal, I can go to BCD. Okay? All right, let's keep moving on. And here you go. This is the this is the big chart. This is table 1-4. And I don't know if, is this 1-5? Yeah, that's the ASCII. So 1-4 and 1-5 are ones that you want to look at and ponder and just see how things change as you count. Because this one has all the number systems here. It's got decimal, binary, octal, hexadecimal. So, you know, you can easily convert numbers from 0 to 20 into a different numbering system. Okay? But like on the lab 1, I wanted you to go through the process of writing this stuff down. And, you know, one of the things I go out and research is handwritten versus typing notes. So I try to get you to write things out as much as possible, not because I want you to do busy work, but that's what helps you memorize this stuff, okay? To write it down, it helps reinforce it in your memory. To the point where you'll get so good that you can say a 1010, you know that's a letter A, or you know that's also decimal 10, okay? So, here's the BCD equivalent. You can see it counts 0 through 9, and then now this one goes to 1, and this counts 0 through 9, and then this moves 1 over. 1 plus 1 is 2, and now that's 20. Okay, so the other non-weighted system we're going to talk about is the ASCII code, American Standard Code for Information Interchange. And that's how we represent our alphanumeric data, how we represent our punctuation, all that good stuff. It uses 7 bits for all of the different keyboard entries that we might have. Okay? And this is what it looks like. So here you see we have all of the alphabet, right? The Western alphabet here, A through Z, capital A through Z. Then you notice we also have the lowercase alphabet, lowercase a through lowercase z. Because the computer is not a human. It doesn't understand language. It doesn't understand what a capital A any more than it understands what a lowercase a is. So you have to have 2 separate identifications for each, okay? Because it's not going to be able to distinguish, oh, that's just capital A. It doesn't know what that means. You have to tell it. So there's a separate symbol in this chart for everything, okay? Even all of the white spaces, like the delete, that's actually a white space. The tab is a white space. Enter is a white space. The space bar itself, when you tap it, that's a white space. And you can see down here, here's backspace, BS. That one's up here. What's another one? Space bar, SP, that's 20. And yeah, so you can see all of that stuff that happens in a computer, it has to have a binary equivalent somewhere. And I say binary equivalent because ultimately that's what computers use as binary language. Even though we can talk about things in terms of hex, it still sees ones and zeros, and that's it. Okay? So you can see here the most significant bit at the top and then the least significant bit over here at the left. So it's a 7-bit number, and this group of 3 is the most significant bit out in front, most significant bits out in front, and then the least significant bits. So it goes these 3 and then these 4 for whichever one you're talking about. Okay? And so you should be able to, if I give you a string of hex values, or if I give you a string of binary values, then you should be able to decode what the message says. Okay? So let's do a few of these. So just very quickly, as we're looking at this here, notice that this is 0 through F. Does everybody see that? It's just 4 bits and it counts 0 through F. This one is 3 bits and counts 0 through 7. So I'm going to do a string of hex numbers on the board, and then I want you to try to decode what my message is. Okay? Hang on one second. Make this big enough for myself here. Okay, so here we go. We've got 3D 42222033. Those are all hex numbers. So using the ASCII chart, all right, what does that message convert to? I'll give you a second to look at the chart because you may have to be flipping back and forth between different windows. Okay, so again, that's a string of hex numbers that if you use the ASCII chart, you should be able to decode. It's just 5 characters. Go ahead and type it in the comments if you got it. First one is 3D. Second one is 4-2. I'm doing this out of view because I'm putting the answers on the board. So 4-2. Okay, I'm getting ready to reveal what you should have so far. Oh, he's saying, could you go back to the ASCII chart? Oh, there it is. It's showing it, yeah. Yes, I can go back to the ASCII chart. So if you have those written down, then go ahead and try the next ones. So the first one is an equal sign. The second one is a capital B. Okay, see if you can get the other three. Okay. Yeah, I was still on the live view. Sorry about that. Remember, across the top, just read that as 0 through 7. And then on the side, that's 0 through F. So if it's a letter, just remember, it starts at 1010. That's A. I just typed in my answer. Okay, let me flip back over now. So there we go. So 3D, if we go look here, 3, so 0, 1, 2, 3. And then D, come all the way down here to 9. So this one, remember, this is A, B, C, D. So that is the equals. All right. Now let's go back. The next one is a capital B. I'm saying it's 4, 2. So let's go back to the ASCII chart and look at where 4, 2 resides. So 0, 1, 2, 3, 4. So it's 1, 0, 0. 4, and then 2. There's 0, 1, 2. That's capital B. All right. Let's go back and look at the next one. The next one is 2, 2. All right, so that one's at the top. So 0, 1, 2, and then 0, 1, 2. That is the double quotes, right? You have to distinguish between a double quote and 2, 7, which is a single quote, right? And then you have a comma down here at 2, what is that, 2D? 2C, yeah. All right, so all those characters have to have a reserved number for them. All right, so let's go back again. Now we've got 2, 0. This is a common one. You'll want to commit this one to memory because I'll ask on the quiz and the exam probably about this. So 2, 0, the reason I say memorize that one is because that's the space. So if I write a string of characters, I might have multiple 2, 0 hex values in there. Okay? So that is the space. All right, let's look at the very last one. 3, 3. Let's go back to the ASCII chart. And so 0, 1, 2, 3, and then 0, 1, 2, 3. Ah, it's the number 3. 3, 3 is the number 3. How about that? Okay. So really the whole string is equals B. You can see down here. Let me point to it. Equals B, double quotes, space 3. Okay, which is not really a message. I'm just saying that's what that string represents. Okay, if you were to, when the computer reads these values, it translates it as it okay, that is this character. That's this character. That's this character. That's this character. Okay? Any questions on this? Oh, Steve said the double quote looked like a dash on my screen. Yeah. Uh, like I said, this is in your book as well. This is table 1.5 out of your book. And if you just search ASCII code chart, there's going to be a million images in Google that pop up from various places. So, sometimes they have the most significant bit on the left. Sometimes it's backwards. Sometimes they don't even have the binary. They just have the hex. All right. Any other questions? Okay. Well, then let me do something else here. I'm going to, while I have the board up here, and it's still up, which is good, I'm going to pull this up on my screen. And I want you to go the opposite direction. I'm going to give you a message, or I'm going to give you a string, and I want you to convert it into a string of hex values. Okay? How about this? Okay? So that says digital is fun. Okay? So convert that into a string of hex numbers. And this is only one space. And that's only one space. Okay? Otherwise, there are no other spaces. Okay? So give that to me as a string of hex values. And you can double check against my answer. Okay, how we doing? That I just now got done doing it, so let me give you my first couple here. I'm going to type them in the comments here. So first 5 that I got were 4, 4, 6, 9, 6, 7, 6, 9, 7, 4. Okay, so you can see if you're on the right track or not. Okay. I'm going to go ahead and write that up here so you can check and see. So capital D is 4, 4. Lowercase I, 6, 9. Lowercase g, 6, 7. Lowercase I, 6, 9. Lowercase t, 7, 4. Lowercase a, 6, 1. Lowercase l, 6, c. Space is 20, or 20, excuse me. And so this is digital space, and then the lowercase I again is 6, 9, and then the S is 7, 3, and there's another space, and then lowercase f is 6, 6, lowercase u is 7, 5, lowercase n is 6e. The exclamation point is 2, 1. So this is digital. There's a space here. Lowercase I, S, space, F, U, N, just like that. Okay? So C says, I'm confused. The 2 numbers on the chart are hex. I'm converting them into hex in my head. So I said, remember, the top is 0 through 7 in binary, and on the side it's 0 through 1, 1, 1, 1, 0 through 1, 1, 1, 1, which is just 0 through F in hex. So look at everything on the left-hand side as 0 through 15, or 0 through 9, and then A through F. Does that make sense? Type that out here. 0, 0, 0 through 1, 1, 1 as 0 through 7, and the side rows 0, 0, 0, 0 through 1, 1, 1, 1 as 0 through F. Okay. Anybody else? Any questions? Okay. Just double check here, make sure nobody has anything. Again, if you have any questions, just go ahead and throw it in the chat. All right. Okay, very good. He said it helps. Okay, so anyway, yeah, so you use the ASCII chart to go either way. And so then I could do the same thing where I give you a string of... Oh, yeah, sorry. I just didn't want there to be a bunch of dead air. I'll do a shorter one. How about that? Maybe that one was a little too ambitious, because it took me, 4 or 5 minutes to do it myself. So, okay, let's go ahead and try a different one. Okay, how about... in semesters past, my students from other countries always love soccer, but they don't call it soccer, they call it football. So let's do, I'm going to do a capital F, foot, ball. How about that? Okay, I'm going to do it on my pad as well. And then we will compare answers. Okay. If everybody has that, I'm going to go ahead and flip back to the ASCII chart. So just capital F-O-O, and then all lowercase football. The only thing that's capitalized is the F. Okay, here we go. Yes, football. So I'm just typing here that mine matches. John had a string of numbers there, and Steve has a string of numbers there, and it looks like mine is going to coincide with John's, I believe. So let me go ahead and put mine up here. Okay. So let me come back to the board. So the capital F, all right. So remember, the most significant bit is what comes first, all right? And so the capital F should be, you go 4 over and 6 down, okay? So that's 4, 6, okay? The lowercase o, if you go 6 over, and if you go F down, or the very, very bottom, 15 down, that's going to be 6F, 6F, right? Those two. The lowercase t should be, if you go over 7 and down 4, so that is 7, 4, okay? So that's the first 4. Okay? Let me see how we're doing in the comments here. Okay. Can I continue with the answer? Or does someone need more time? Okay. All right. Well, I'll go ahead and continue then. So then the last four letters, if you look at your ASCII chart and go over 6 and go down 2, you'll get the lowercase b. So that is 6, 2. The one right above it is 6, 1, which is the lowercase a. And then the lowercase l is over at 6c, 6c. Okay, so that's 6, 2, 6, 1, 6c, 6c. Okay? All right. David says he has like a close to a minute delay. I'm following along though. Okay. I've tried to set the latency as slow as possible. So I don't know if they do that for security reasons or what, but anyway. So anyway, that's just a simplified version of that. Okay, so if we go back over to, the chart here, you can see, so the capital F. So if I go over 0, 1, 2, 3, 4, and then 0, 1, 2, 3, 4, 5, 6. So there's 4, 6. There's the capital F right there. Okay. The lowercase o is all the way down here. And so down here it's 1, 1, 1, 1. We know that binary to hex, that is a letter F. So that is 6F. Okay. And then there's two of those. So 0, 0, or 00, and then lowercase t. So that's 7 and 4. Okay. So again, remember I told you that we have that that number game from Whisk Online. If you should start to easily spot these if you're working with the numbers. Okay. So go back and do those games because they help you recognize this and it'll make more sense. Okay, because right now it probably just looks like Greek and you don't have any of this stuff memorized. But try to start, and those games are a great place to start that I showed you about. And if you missed it, just go back to last lecture. Okay, any other questions? All right, well, let's keep moving along. All right, am I on? Yes, I'm on. It says, because digital systems must work with ones and zeros, learning the different numbering systems is important. Which system is used is determined by how the data was developed and how they are to be used. Several number system applications follow. So I'm not going to go through all of these, but I like using this one right here. Okay, so here we've got 4 tanks, and we're monitoring these. Okay, and we've got this pressure sensor, and I'm assuming it's a high limit switch. In other words, if the pressure exceeds a certain pressure, then it will trip the sensor and go high. I'm going to assume these are all normally open without knowing anything else. Maybe it'll tell me that they're all normally closed, but I'm going to assume they're all normally open. So at rest, if they haven't been tripped, they are off. And so I would expect if all of these pressure and temperature sensors are not showing any signs of worry, that this should all be 0, 0, 0, 0. So you have a string of bits here, 8 bits, that can be sent to a computer system. Okay, so you have to be able to interpret what that means. Okay, so let's look at the next slide here. It says if the computer read a binary string of 0010 1000, what problems exist? Okay, so that would be 0, 0, 1, 0. So pressure C must have tripped and went high. And then the last 4 are 1, 0, 0, 0. So the pressure in C and in tank B must have tripped and have gone too high. So we can use that now in a computer system, that can detect that and then possibly set an alarm or shut something down, but it'll let somebody know that there's a problem. Okay, so we're constantly monitoring these 8 bits for changes. Okay, so I always think that's a pretty good one. All right, and so now here's the next one. If the computer reads a hex value of 55, what problems exist? Well, if we convert that into binary, remember hex to binary is just a direct conversion. So what is the 4-bit equivalent of 5? It's 0101. What's the 4-bit equivalent of 5? It's 0101. So here is our binary string. That indicates that all the tank temperatures are too high, right? 0, 1, 0, 1, 0, 1, 0, 1. That means all the temperature limit switches are high, and you've probably got some kind of a problem, okay? But that's a way that we can use, between the different numbering systems here, okay? It says, if the temperature and pressure in tanks B and D are too high, what hex value is read by the computer? It said the condition that would produce a digital output is 1100, 1100. So it says, if the pressure in tanks B and D are too high, temperature and pressure. So that's these two, and that is these two. So it would be 1100, 1100. And if we convert that to hex, this is C and this is C. So the answer is CC. CC and hex, that's what that means. If you're wondering what that H is off to the side. That's the same as me putting a 16 in the subscript. All right. It says maybe we add decimal to the chart. I mean, here's the thing is you can take notes and rewrite the chart however you want. Or if you just want to, some quick notes to help you remember how to convert between, 0, 1, 0 is 2 and 1, 0, 0 is 4. And so maybe you have a little chart that sits next to you that you can easily convert between the two systems. Because it's not really decimal that you want added. It's really that you want the hex added. The hex is what makes it easy, because then if I say 7D, well, then you just go over to 7 and then you go down to D. So if you want to rewrite that or write a little note to yourself on how to make that easier, that would be your best bet. Okay? Now, when it comes to the exam, I'm going to assume that you are going to have a copy of the ASCII chart. So you don't have to use the one that's in the slide if you don't want to. You can go on Google and find your own. Like if you find one that's got the hex chart in there, by all means, bookmark that and then keep it out while you're working on this. Okay? All right. I believe that takes us through the end of this. Okay, so let's just recap real quick. So numerical quantities occur naturally in analog form, but must be converted to digital to be used by computers or digital circuitry. Binary number system is used in digital because the ones and zeros are easily represented as I always say, ones and zeros, on or off, yes, no, true, false. To me, all of those things just mean discrete. There's only 2 states. So which output 0 volts for 0 and 5 volts for 1. Okay, so that's the range between 0 and 5 volts. So the way that we recognize a high is if we measure 5, and if we recognize a low, then we measure a 0. So these digital systems are only either outputting 5 volts or 0 volts when it comes down to it. But we just go ahead and in 112 here, we just assume that those are just zeros and ones. Okay. When we get into 122, we'll see how this is a little bit different than being this straightforward. But for this class and for your quiz and the exam, 0 volts and 5 volts are the 2 different voltages that we use. Okay? Any number system can be converted to decimal by multiplying each digit by its weighting factor. So we learned how to go from, between all of them, right? Binary, hex, octal, and decimal. And now we've learned BCD. So if we need to translate into BCD, you always have to go through decimal first. Okay? And we use successive division to go back the other way in some cases. And so all of that's covered in that very first lecture. All right, so let me get out of this. And it should go ahead and pick up the chapter 2. Bing, it did. All right, way to go. All right, so now we're going to talk about getting into a little bit more logic and talking about what a signal is and how we can use switches to route that signal, so to speak. Okay. So I will just go ahead and keep going here, and I've got the chat open here to see if anybody has any questions. All right. So we like to look at everything in what is called a timing diagram. And in a timing diagram, you're always looking at two things. The x-axis is time. And so as you go in the positive x direction to the right, you're going positive in the positive direction for time. So you can look at a signal over a certain period. Okay? And then you can see here the voltage levels, what I would also call the amplitude. And so you've got the two different voltage levels here. So over time, however long that takes here, we went from 0 to 1 to 0 to 1. Right? So in this class, if we were in class, we could look at an actual physical circuit hooked up and look at the output of one of these gates and see a signal like this. Okay? An oscilloscope is simply a way to view something, an XY plane, and it's great for plotting time versus amplitude. Okay, that's what it does. So we also have in our Quartus that we're going to be using, it has a simulator which will mimic what an oscilloscope would see. And so you'll get to see that as well. Okay, but this is how we look at our digital signals. How do they change over time? And at any point in time, what are different inputs doing together to make a change? Okay, and that's when we start looking at the gate logic. So for all periodic waveform, and this goes for sine waves and cosine waves and tangents and all of them, okay? All periodic waveforms are similar in the following manners. They're all repetitive. In other words, they repeat over and over and over. They have a specific time interval for one iteration, okay, one complete cycle, and then the successive pulses are identical in that repetitive. You can't have a sine wave and then the next period you have a cosine and the next one you have a sine. All right, it repeats over and over and over. That's the definition of a periodic waveform. So in your analog classes, when you get to the AC circuits, you'll use sine waves. When you take DC analysis, there's no point in looking at it because it's just a constant signal. So if you were to look at a DC signal, right? Let's say we're looking at the DC power supply and it's a 9-volt supply. It's just going to be 9 volts all the time. And then maybe, a month from now, it's got a little bit smaller voltage, but it's such a small decline that you can't even tell what the slope of the line is, right? So it's just a constant output, whereas this can change, right? We've got inputs and outputs that are changing all the time between these two different voltage levels, okay? So the period is the time it takes for one cycle to complete. And then, as you know, frequency is the inverse of that. Okay? So let's look at a couple examples here. So if a clock waveform has a period of 2 microseconds, so a clock waveform would mean that it looks like this. In other words, this would be one iteration, right? And then this is another cycle. So 1 cycle, 2 cycles. Okay? And so wherever you start, if you start down here, then 1 full cycle is right back down to that point. So if you follow my cursor there, this is 1 period right there. Okay? This is 1 period right there. Okay, so there's 2 periods that I see on here for this clock waveform, if that were a clock waveform. So if it has a period of 2 microseconds, in other words, it takes 2 microseconds to complete 1 cycle, its frequency is found as 1 over that time. Okay? So if we take 1 over 2 microseconds, now we get something that's measured in hertz. Okay? Hertz is basically cycles per second. In other words, when we're talking about these two terms here, the period is how long it takes to complete 1 cycle. The frequency is how many of those cycles fit inside of 1 second. That's essentially what frequency is, okay? How, using 1 as a base, how quick is this signal, okay? And so we take 1 divided by 2 microseconds and we get 500 kilohertz, okay? Kilo is 1,000. So this is really 500,000 hertz, all right? So that's the frequency of that waveform. The higher the frequency, the shorter the period. In other words, it doesn't take as long to complete one. Okay, let's go the other way. We have a 4.17 megahertz. Mega is million, 10 to the 6th. So that's 4.17 million hertz has a period of, take the inverse of it, so 1 over 4.17 megahertz, and you get brought back into seconds. Okay, and that converts to 240 nanoseconds. Nano is -9. Okay, so this is 240 times 10 to the -9 seconds. That's what this prefix is. Okay, K in front here means times 10 to the 3rd. Mu, or U, out in front here means 10 to the -6th. So this is 2 times 10 to the -6 seconds, or 0.00002 seconds. Okay, but that's, the reason why we use these Greek prefixes is because I don't have to say 0.000002. Okay, I just say 2 microseconds, and you go, oh, that's 2 millionths of a second, and you can quickly qualify it. Okay, so leave your calculator in engineering mode the rest of the time you take classes. All right, if you need to know where that is, send me an email with your calculator number, and I'll tell you how to set it up. Okay, so it'll always output something in engineering notation. All right, so here's what it is. Some of these you already know, right? If you buy a computer, more than likely you're going to look at how many terabytes your hard drive is going to be. You may still just need gigabytes, right? But what does that mean? That means 10 to the 9th bits. That's a billion, okay? So this is 1,000, million, billion, trillion. Okay, if you go in the opposite direction, if you move the decimal away, now this is 1,000th, 1,000,000th, 1,000,000,000th, 1,000,000,000,000th. Okay, if you want to think about it like that. So these are thousandths, millionths, billionths, trillionths. Okay, now in this class I don't think we do much with the pico, and really this is the only section where we use these anyway, because most of the time we're designing digital circuits, and so there's not really a place for the engineering prefixes. But when we're talking about doing these type of calculations, it's crucial. Okay, so try some of these out. We can go ahead and do a couple of these on the board here. Let me go ahead and switch back over. So I have my clock waveform has a period, and I use capital T for period. So capital T, the period is 1.16 nanoseconds. Okay, so if I switch back over here, nano. The way I always remember nano on the negative side is that nano starts with N and 9 starts with N, and that's how I always did. I always used to get pico and nano confused, and so nano is 9. There we go. Vault door slammed down shut on that one. So nano 9. Okay, so what this means is 1.16 times 10 to the -9 seconds. Okay, so if I want to find what the frequency is of this, I take 1 over the period, which is 1 over 1.16 nanoseconds. Okay? So do that calculation and see what you get. Nano is getting on with the program. That is a quick period, so this should be a pretty big frequency. Get my calculator out here. So 1 divided by 1.16 e -9. All right, let me come back over to the chat here, see what people are getting. Frequency. And give it to me with engineering notation. and just give me 3 significant figures. Let's see what you come up with here. I have my calculation, and I'll say that mine is in the megahertz range. Anybody? It's in the megahertz range. All right, so I got 862 megahertz. Okay, my calculator gave me 862.069 times 10 to the 6th. Okay, and so this translates to mega, right? And this is hertz. And so I rounded 3 significant figures here. Okay, so 862 megahertz. Yep, Kofi got it. So the key to doing this is knowing how your calculator works. Okay, if you punch this into your calculator wrong, it doesn't matter if you know how to do it or not. You need to know how to do it on your calculator. And so again, there's only going to be a few of these that you're going to have to worry about anyway. It's not like you're going to have to use this for the whole class. Okay, but for right now, I mean, you know, you got to plug this in, especially since it's in the denominator. You really want to use your parentheses if you're using a TI 30 series, especially. Okay. So he says, I think I'm typing it in wrong. So I got a couple of correct answers there. Very, very good. Okay, now I'm going to go the other way. One of my favorite radio stations is WIBC, and they broadcast on 93.1 megahertz frequency. Okay, so when you tune into the radio, FM 93.1, 94.7, or 93.9, which is a great one, you are tuning into a megahertz frequency. If you're on the AM dial, so like I like 1430, that's kilohertz. Okay, now I realize that means 1.43 megahertz, but the AM dial is all set up on kilohertz, so that's why you say 1430 or 1260. That's 1260 kHz. Okay, so 93.1 megahertz. So I want to know the period. This is how I type it into my calculator here. Let me get back over to us. So you can see there, 1 divided by 93.1 times 10 to the 6th gives me 10.7 nanoseconds. Nano is -9. Okay? So just to show you how I'm doing that on my calculator. Okay, so I got 10.7 nanoseconds. Okay? Let's see if anybody got that. Yep, Kofi got it. Very good. All right, so it seems like you guys are following along. You may have already done something like this if you've had circuits classes or electronics classes before, because this is a common calculation. So that's all we're doing. It's just going from one to the other. If I give you a frequency, can you give me the period? And if I give you a period, can you give me the frequency? Okay? So Abdullah off by a power of 10. So you might want to check how you punch that in. Okay? Here's the other way I could punch that in. Okay? I'm going to focus in on this. So if you're saying, okay, that's great, I don't have your calculator, how can I punch it into mine? Then I would punch it in like this. You probably have a times 10 to the x key. If I can get this to focus in here. There we go. So that's another way to do it, right? 93.1 times 10 to the -6th in the denominator. And notice I have to put the parentheses around it. Okay? So that's another way to do it. The way I did it above or the way that I typed it in right there. All right. Well, if nobody has any questions, I'm going to keep going here. So let's switch back over. So again, the vertical scale of an oscilloscope, or a timing diagram for that matter, represents amplitude or voltage. What's the horizontal scale represent? That represents time. Frequency, again, the distinction between the two is period is how long does it take it to complete one cycle. Frequency is how many of those cycles can you fit inside 1 second. Okay? We already did some of these calculations. I'm just going to keep going here. And let me come back and double check our syllabus. Says that we go through series, parallel, and switches. Okay. I think what I'm going to do is just go ahead and finish off Chapter 2 today. And then we'll just start with Chapter 3 next time and just go straight into the gates. Okay? So, if we're going to do a serial representation of a binary number, let's say, or a string of binary digits, we typically transmit them over a single conductor because it's a lot of money. You know, it would be, you can't even imagine how quick we could make communications if we were able to transmit like 8 lines at a time. So when you have your fast speeds at your home with your broadband internet, that's all being done on a single conductor. Right? Now, they're very smart in how they use that, but it's still a single conductor. That's serial communication. That just blows my mind. Imagine if we had 8 of those running at all time, how fast everything would be. But then think about, you know, the entire the infrastructure for all of broadband would be 8 times more expensive because you'd have more material costs. Okay, it's also room for other things to go wrong too. But it would be incredibly fast. We do pretty good just doing serial. All right, so serial means that you're going through one single electrical conductor. Okay. So, some high-speed serial communication standards are these up here, and Ethernet is what we use, obviously, and then USB. You know, it's in the name, Universal Serial Bus, right? And so, you know, it's different speeds depending on the version, typically in the hundreds of megabits. Well, now that we're into USB 3, since Kleitz wrote that book, we are now into the megabytes per second. I think the baseline of the USB 3 is what, 646 megabytes per second? And it's bytes, not bits. Okay, USB 2 is still down. It still does pretty good in its transfer speeds, but you know, you have to remember how far USB technology has come in such a short time. You know, I still remember zip drives, for that matter. I still have my zip drive somewhere, 256 megabyte. I thought I'd never have to buy another. You know, I was going to have so much that it was kind of a waste of money for me to get something so big. And then I filled it up super quick when Napster came out, but so did everybody, right? So anyway, so if we're going to represent it, we can represent it on a timing diagram. Okay, so if we have the binary numbers 0110, 111, I'm sorry, 1100. It says note that there is 1 bit per clock period, and the bit-to-bit change occurs on the falling edge. And that's something we'll talk about in later chapters as to why it only happens on the falling edge when it changes. Okay, it's intentionally set up that way in some circuits. So here we have the clock pulse, and so when it changes, boom. Now we're going to clock in another one here, so we can represent this. You see how it looks like it's backwards, right? It's because the least significant bit is what comes out here first, right? You see that? So if we were going to shift this from like a shift register or something, this information, then you always send out the least significant bit first. So in time, it occurs ahead of the most significant, and when you read it left to right, it looks backwards, right? The number is 01101100, and it's listed down here as 00110110, but that's because the most significant bit is the last one to be clocked out. Okay? So I could ask you something like that on an exam too. You know, give me the serial representation of this binary number, and you would just have to remember that it has to be backwards when you write it out here. Okay? Parallel representation. Now we're cooking. This is what you'll find on the inside of your computer. If you have you know, a lot of bus systems that use like 8 wires at a time, and you know, but you're only traveling what, maybe 12 inches from component to component. So even though it's more expensive, you're traveling a very short distance. But computers take advantage of that for sure. But it's because it's very, very fast. All right, and so. There are some interfaces that we used to use. We don't really use these anymore because now everything is USB. Okay, but parallel used to be, you know, I don't know if you remember these gigantic printer adapters, but they were, I forget how many pins they were, but you know, you were kind of out of luck if one of the 64 of them bent or something and came out. You know, the entire thing was ruined. So you had to be like picture perfect when you plugged it in. But now we have USB, and you can fumble with it in the dark and plug it in backwards 10 times before you do it the right way. So they're a little bit more durable now. And again, you know, we're talking about you know, bytes per second now. So this is a step up. But again, we've got serial that does more than this right here. Okay. So we are getting on with the program these days. So let's look at switches in circuits. Switches in circuits. Check back here. And okay, no questions, so we'll just keep right on rolling. So a switch, if you are familiar with electricity at all, makes or breaks a connection between conductors. We have light switches, we have all kinds of different switches that turn power on and deliver power to a device or cut power off to a device. And we, in the electrical world, in the electrical engineering world, like to use diodes and transistors to accomplish that type of switching. We call them electronic switches. Okay? Now, if you have an ideal switch, it has no resistance, it doesn't drop any voltage, and it just magically opens and closes. Okay? And it doesn't distort the circuit at all. But that's not the case. If you're using a diode, then you know that you're going to drop at least 700 millivolts. Okay, so you're going to have to account for that in your circuit. Okay. And this is talking about the different logic levels, right? So if this is my output, and let's say this is connected to either an LED or maybe this is the input of some other gate over here, okay? And so if we want to have a high on this, if we want 5 volts available, then we could have a selector switch that was connected directly to 5 volts. And if we wanted a low output, then we could move the selector switch and connect it directly to ground and guarantee that we have a low. So here we can manually change the input, okay, just by having a 5 volt attachment and an attachment to a ground. Okay. So if you configure more than one switch in a system, you've essentially set up a control mechanism that's either going to be in one of 2 logical orientations. Okay, one way to do it is what you see up here. Okay, so for this lamp to turn on, remember, you can't have any circuit current if you don't have a complete path. If you have an open, there is no circuit current. So to make this lamp work, listen to how I say this, switch 1 and switch 2 have to be closed for this to work. Okay, the key word there is right in the middle. It's and. This is essentially the logical, the switch representation of a logical and. Okay, this will not turn on unless both of these. It doesn't matter if just switch 2 is on. It doesn't matter if just switch 1 is on. It has to be both of them for this to turn on. That is an and situation. Okay, the other operation is what you see up here. Okay, so where you have the switches wired in what's called parallel. These are wired in series. These are wired in parallel. So when the current comes up to this node, it's got a choice. It can go through this branch, or, key word there, or it can go through this branch to illuminate the lamp. It doesn't have to go through both of them. So in this situation, I would say that either switch 1 or switch 2 or both switch 1 and switch 2 will activate this lamp. Okay, so there are 3 different conditions that will make this thing illuminate, whereas in this case, there's only one combination that works, right? Because the combinations are off, 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 on, off, or on, on. And the only one of those 4 combinations that makes this turn on is the 1, 1 situation. Over here you have 0, 0. That'll keep it off. But what if you have 0, 1? Well, now you have a path to turn it on. What if it's 1, 0? You still have a path to turn it on. What if it's both? Well, pick, right? And so both of those will deliver power to the lamp. Okay, so that one has 3 out of the 4 that will give you a high. All right. Now, think about these. I always try to use the example of your vehicle. Okay. An and situation. I had a student a few years back. It's been about 4 years now. But he was from Egypt, and when he got here, the company that he worked for bought him a brand new car. They said, go out, we don't care what it is, just go buy yourself a brand new car. And so they bought him a brand new Mercedes, okay? And so his and situation was, if he wanted to start the car, there had to be 3 different things that happened, okay? He had to first have to have his key fob inside the perimeter of the vehicle. That's the first thing that had to be done. The second thing was he had to be sitting in the driver's seat, because there's a pressure switch that determines whether or not somebody is actually in the vehicle ready to take control of it. So that has to be on. And then he also had to push the button while his foot was on the brake. So there was actually 4 things. Okay, the pushing the button was the very last thing. And so once he did all 4 of those things, it would start up. Okay? But if he just did any one piece of it, or just 2 of them, or just 3 of them, it wouldn't turn on. Okay? And so essentially what it's doing is it's making you, okay, are you sure you want to turn this on? I've got somebody sitting down. The key fob is in the car. I see that there's somebody pushing the brake, so I know it's not just something sitting on the front seat. And now I'm going to let the push button activate the vehicle and turn it on. Okay? The other car situation where I described the or is your dome light. Think about this as your dome light. What can turn your dome light on? Well, one thing is if you have your driver's side door open, it will turn the light on. Or if you have your passenger side door open, it will turn it on. Or there's actually a switch inside your vehicle that will manually turn it on right by probably by the instrument panel where you drive. Or a lot of times if you have an overhead light, there's another switch on the light itself. So that would be 4 different situations where you could turn that light on. And it doesn't matter if you have a combination of them. All you need is just one. Either one or some combination of all of them. Okay? The only time that it will be off is if they're all off. All right? So hopefully that, you can see the difference here between the and the or. All right? If you can pound that into your head, all the rest of the gates should be pretty straightforward. But we're not even using the actual logic symbols yet. We're just talking about the gates. Okay? Or using switches to create that logic. Excuse me. Okay? So again, we can use diodes as switches. A diode is nothing more than a semiconductor device. It's got a p-n junction inside, and essentially you can think about it as an electronic check valve. It only allows current to flow in one direction. It will not let it flow in the opposite direction, so that's the check valve version of it. You can see here, this is an example of a check valve where it'll let water flow this way. The flap will come up and let it flow, but if the water tries to rush in the other way, this flap will close and prevent flow in the other direction. That's what this does with electrons. So it allows it in this direction, but it blocks it in the opposite direction. Okay, so that's a automatic switching mechanism in the circuit. Okay. Let's see here. And so using it as a switch, it has to have at least 700 millivolts across it before it will activate and conduct current. Okay. If it does not have 700 millivolts, it will not conduct current. Okay, so that's why I'm saying it's not a perfect switch. You do have to satisfy this 0.7 volts before it will activate. Okay, and so now here we can see we can use those to our advantage in these different little circuits here. Okay, so it says determine if the diodes shown in figure 226 are forward or reverse biased. Okay, so this one, because of the orientation of the battery, I know that the current's going to flow from positive to negative. And so this first one here is in forward bias, and I have current flow, and this thing will turn on. Now that I have the battery in the opposite direction, the current's going to want to flow this way, but you can see it's going to get stopped by that diode. So I have no current flow, which means I have no illumination of this light. Okay? And so you can orient these diodes in ways that you can make AND gates and OR gates. Okay? And so you have a 0, you have a 1 here, and you have a 0 here. This one is still going to have 5 volts available because this one is on. So D5 is on, this D6 is off. Either one or both will give a high on this output here. For this AND gate, you want to drop that voltage. So if these are both 0, or if only one of the two, okay, so here we've got it's essentially going to have the full voltage drop across here. Okay, so it's going to drop it. It's connected to ground. This is going to be 0. If this one is 0, then it has a place to drop that voltage, and the output will be 0. But if these are both high, it's got nowhere to drop it, and so this will also be high. Okay, so you have to have both of these on for this thing to output a high here off to the side. Okay, and this is not an analog class. Students get very, very confused about these diode circuits, and so I'm not going to focus a whole lot on them. Okay, but we can represent these switches with diodes. We can also use transistors as well, and again, this is not a transistor class, but you can use bipolar junction, which is like your standard NPN, PNP transistors, and then you have your MOSFET transistors as well, and the FET just stands for field effect transistor. Okay, so you may have a MOSFET amp in your car, let's say. That just means that you have these type of transistors powering it. So let's look at that. So one type of an IC chip is called the TTL circuit. Okay, and that stands for transistor logic. And over here to the right, you see that there's an inverter. And so here's the output. Here's VN. Here's the output. Okay, and all it does is it's inverting. So if there's a 0 here, the output will be a 1. If there's a 1 here, the output will be a 0. That's the definition of an inverter. Okay, we'll talk about that later too. But that's all it does. It converts a 1 to a 0, 0 to a 1. So you have this totem pole output. You have the transistor stacked onto another transistor. And that's where you get this TTL, transistor logic, because you have the totem pole output here. Okay? So the way that you get a high or a low on the output in that IC chip is that either this one is on or this one is on. If Q4 is on, that means it's going to short between here and here, and it's going to output to here because this one is turned off. Okay, and so it's going to output through this way. If Q4 is off and Q3 is on, then it's going to sync the signal back through here to ground. Okay, and so that's how you would get a high or a low. So it's not that a magical 1 or a 0 appears on the output. You're either sending a signal out or you're syncing a signal back through that bottom transistor. Okay, and we get more into that in chapter 9, which is in 122. But that's really what's going on. Remember I showed you the chip earlier, that IC chip in the Zoom meeting, right? That's got the black rectangle and it's got the pins on it. That's what's going on inside the box. That's just, nothing more than a bunch of resistors and transistors and diodes. That's all it is. At the end of the day, even though we're talking about digital, all electronics are analog. When you break them down to their base components, it's all comprised of diodes and resistors and switches. So, digital is something we're superimposing on analog systems, if you will. Okay? And so this is what it looks like inside that IC chip. And so, between pins 1 and 2, I can put my input in through 1. Those internal transistors will convert that into a 0. Or if I put a 0 on the input here, it'll convert it into a 1. Okay? And I've got 1, 2, 3, 4, 5, 6 of those available on one chip. Okay, so that's pretty powerful. So 14 is always the ground, and 14 is always the power, and 7 is always the ground, right? 17 power, 7 ground. 14 power, 7 ground. Right? And so this is what we call a 7404. If you have your book, I'm going to switch back over to me real quick and see if we can pick this up. Because inside your textbook, this thing, right? Inside the textbook, it's got all of these. Okay, and I don't know how well you can see that. I don't know how well it's going to focus on here, but here's the 7400, 7402, 7404, 7408. It gives you a pinout of all these different standard TTL chips. Okay, and so you can look through those and see how they're oriented. Sometimes it's not always in this orientation where 1 is always an input. Sometimes it's backwards, and maybe 2 is an input and 1 is the output. That's why it's so important to have the pinout. Otherwise, there's no way you're ever going to know where to put your inputs and outputs because there is no marking on it. The only marking on it is what the model number is. Okay? Any questions? Okay, you guys are stuck with me pretty good here. All right. There also is what's called the CMOS IC chip. And so you see this one. The only difference between this one, well, there's a lot of differences, but if you just look at their pin out, this has 14 pins, and the CMOS has 16 pins. Okay, so it has a few that it doesn't use, like 16 and 13, and its power and ground are on different pins, and so you just have to get the pin out to figure out which one that is. Okay, now CMOS are typically sometimes they're a little bit more expensive, but that's because they're faster and they typically use lower power. They run off a smaller voltage. So the high voltage output, so like on a TTL chip, if I were to measure the high voltage output, as long as it's above, I think 2.4 volts, it's considered a high. Okay? If you were to look at this, its high output is maybe only, the threshold is a little bit different. Okay, so it might accept a high at 2.0, okay, whatever it is. So it's a little bit different in how they operate. Now, the people who manufacture CMOS chips went, well, if people are going to start replacing their old TTL chips with newer CMOS chips, newer technology, then we need a way for them to go right on top of each other. So there are now CMOS chips that are 14-pin that have a direct footprint that matches this. So basically they cloned the TTL version using their CMOS technology inside, and now you can directly replace your TTL with a CMOS and not have to worry about the pins being in different places. Okay, and so those are the way that you would tell that would be, here these are all 4000 series, so that might be like a 4001 or a 4010. The TTL is all 7404, 7408. If you see a 74HC 04 or 08 or whatever, that means that it's a CMOS chip with a TTL pinout. Okay, let me see that again. So the HC means that it's a CMOS chip, even though it has this 7404, which is a TTL designation. The HC indicates that it's a CMOS chip with a 14-pin direct correlation to the 7404, like in this case. Okay. Any questions on this? So that's the difference between the two. TTL is a little bit cheaper. It's been around longer, but CMOS in a lot of ways is better because it's lower power consumption. And if you have a digital device, especially a handheld device, that's something to consider because you don't want your end user to be frustrated that your thing keeps chewing up batteries, right? Okay. So, in summary, digital level for 1 is commonly represented by 5 volts, and a digital representation for 0 is 0 volts. An oscilloscope can measure what I call the time analysis. So we're looking at time on the x-axis, and we have amplitude or voltage on the y. Right. And relays capable of forming shorts and opens in circuits requiring high current values but not high speed. So we don't really talk about the relays that much, but Kleitz does go into it a bit. Diodes are used in digital circuitry whenever there's a requirement for current to flow in one direction but not the other. That way you can block and prevent. They also are used for spike suppression, all kinds of things. Diodes are so useful. And then the transistor is the basic building block of the modern digital integrated circuit, which, as you know, is the IC that I keep talking about. It says it can be switched on or off by applying the appropriate voltage at its base connection. Okay, so we're not going to get into the operation as much, but once it's activated, then it turns on. Okay. TTL and CMOS IC chips are formed by integrating thousands of transistors in a single package. They are the most popular ICs used in digital circuitry today. And I would say that when I crack open my kids' electronic stuff that makes noise and lights up, more than likely they all have TTL because they're not worried about speed. And they know the kid's going to leave the thing on anyway. So at that point, it doesn't matter if you got CMOS chips or if you got TTL. And so they just go the cheap route and use the cheapest things that they can. So that's what I found when I cracked those open. But, if it's something that's a little bit more high tech and they want the battery to last longer, then they would use something that consumes less power. Okay? Any other questions? So we actually just covered part of the next lecture, which I'm okay with. It's just going to allow us to do more things in the next lecture. Plus, there wasn't a whole lot left of this one. Okay? So if I have no other questions, then you all are free to go. And let me quickly go back over to the website so that I can show you what's due for today's lab. And my camera went off, so I'm going to have to finish from here. Okay, so I'm coming up to the assignments. So I'm going to do exactly what I did before here. Am I over here? Yep, I'm over here. So I'm going to scroll down to Lab 2. Don't worry about the switches one. I'm just going to go ahead and unpublish that one because that one we would have to do in class. So this Lab 2A codes. All right, I'm going to edit this. And today is the 11th. I'll give you until the 18th to turn this one in. So, submission. online, file upload, due next Thursday. And so again, either print this off, complete it, and scan back and submit, or write out on paper, take pictures, and upload the pictures. Okay, I don't care which way you do it. But this one, let me go ahead and save this, because this one's only front page. The last one was front and back. This one's just front page. So let me go ahead and open this up. And let me get over to my Word scene. And we'll get out of the syllabus. And it should pick up my gray. Oh, come on. You know you want to. There we go. Okay, and so this is what it looks like. So you can just write out off to the side here. So again, I'm using the ASCII chart here, and there you go. There's the hex 0 through 7 on the top, and then 0 through F on the side. So I was doing those conversions on my own on the other ASCII chart that we used. Okay, so again, pretty straightforward. It's just this one page here. Doing a little bit of ASCII work and then converting to BCD. Now you'll notice that only one of these starts in decimal. That means these other 4 here, you're going to have to convert to decimal first and then go to BCD, right? And then the following down here, I give you the BCD, and then you have to convert into these different ones. Now the first 2 are the only ones where I ask you just to go to decimal. Those will be the easiest. The other 3, you're going to have to go to decimal first and then convert. Okay? So, like I said, not a whole lot to this, but just a little bit more work with this stuff. And if I don't have any more questions, then I'm going to go ahead and let you all go. Okay. So everyone is free to go. Thank you for attending. And if you have any questions, just let me know. Okay? I will see you all later. Have a good weekend.